Alright, so in this video I'm going to show you how to determine the rate law and what K is with experimental data. So if you're just given an equation of the reaction, you can't determine the rate law that way without knowing what the mechanism is. You need to know what the slow step in the reaction is. So rate laws depend on the slowest step, and if you have that mechanism and you know what the rate determining step is, then you can just use the equation to figure out what the rate law is. But if you're just given the entire reaction, you can't do that. So if you don't know the mechanism, you don't know the rate determining step, you're going to have to look at some data. So in rate law experiments, what we do is we take the concentration of the reactants, and what we do is we vary one concentration and we measure the rate. And then when we do that, we're able to compare and figure out what the rate of, or what the order of each reactant is, and then we can figure out the rate law. So the concentration of one species will be changed, then the rate will be measured, and then by doing that you can compare. So this is a sample of what data would look like if you were looking at trying to figure out what the rate law is. So you have this reaction right here. So you have your three reactants, and what you did is you changed the concentration of the BrO3, the Br, and the H. And then we measured the rate, so how fast did it take the reaction to go to completion. So if I look, let's look at mixtures A and B. If I look at that, it looks like Br was kept the same, H was kept the same, and then right here, BrO3 was doubled. Well, when that happened, my rate also ended up doubling. So I can use that information to kind of figure out what the order of each of these reactants is, and then figure out the overall order for the entire equation. Alright, so let's look at what happens to the rate when I double BrO3. So I'm going to look at mixtures A and B. So when I do that, okay, when BrO3 is doubled, so the concentration of BrO3 is doubled. So right here, Br was kept the same, H was kept the same, so we only changed the concentration of BrO3. So we have to do that. We have to keep everything else the same to figure out what happens to the rate when I change BrO3. So BrO3 is doubled here. It goes from 0.005 to 0.01. And what I notice is that the rate doubles. Alright, so now I know my rate law looks like this. It looks like K times the concentration of A to some power times the concentration of B to some power, yada, yada, yada. Okay, well, right here, I know that the rate doubles. So the rate went up by a factor of 2. I also know that BrO3 was doubled, so the concentration also went up by a factor of 2. And I know that it's taken to some power. So I need to figure out what that power is. Well, right here, since my rate doubled when my concentration doubled, and I know that the concentration is taken to some power, I can just simply figure out what this is. Well, if it's the same thing, it goes up by a factor of 2 on both sides, then x has to be a power of 1. So these exponents are always going to be either 0, 1, 2, 3 is as high as you will see them go up. So if you know that, you can simply kind of plug it in and just figure out what the power should be here. Since it's the same, it has to be 1. So that means that BrO3 is the first order reaction. So I know that BrO3 has to be taken to the power of 1 because it's a first order. All right, so now let's look at Br minus. So I want to know what Br minus, what order that is. Okay, so let's look at doubling Br minus. So usually when they take the concentrations, they usually just double them. It's the easiest thing to do. All right, so for this one, we're going to look at B and C because Br went from 0.025 to 0.05, so it doubled here. BrO3 is kept the same, H is kept the same. All right, so now I know that my concentration of Br minus was doubled. Let's look at what happened to the rate. Well, it went from 20 to 40 when it was doubled, so that means the rate was also doubled. So that means that Br, the concentration of this, went up by a factor of 2 to some power, and then the rate also happened to double. Well, the only power that could be would be 1. So that means that Br minus would also be a first order reaction. All right, so let's look at H now. Okay, so H right here doubles when I look at C and D. So C, it goes from 0.03 to 0.06, and then the other two reactants are kept the same, so I can use that C and D right here. All right, so concentration of H, I know it's doubled here. All right, so now let's look at what happened to the rate. Well, the rate went from 40 to 160. So that means it actually quadrupled here. All right, so the rate quadruples. If I take 40 and I'd multiply it by 4, it would go up to 160. So I know that the concentration of H was doubled, and as a result, the rate went up by a factor of 4. Well, 2 to some power equals 4. It has to be 2. X to the second power would give me 4. So 2 to the second power would give me 4. So that means that H is a second order reaction. So now I can put all those coefficients together to get my rate law. Okay, so I know that Br minus was a first order. I know that Br minus was also a first order. I know that H plus was actually a second order. So I can use that information to figure out what my rate law should be. So my rate is equal to K, which I still don't know, multiplied by BrO minus to the first times Br minus to the first, and then H plus to the second. Okay, so simply taking the data, you can figure out, okay, what happened to the concentration of 1, then what happened to the rate as a result of that. And then when you do that, you can figure out what that power should be. So really you're trying to figure out what order reaction would each reaction or reactant have. All right, so let's look at something else. All right, let's look at this reaction. So we're going to deduce the orders of the reaction. We're going to find the overall reaction, the overall order, and the actual rate equation. And then I want to know the value and the units for K, for the rate constant. So we're going to do the same thing. We're going to look to see what's happening to X, what's happening to Y, and what happens to the rate as a result of that. So let's look at X first. So in experiment 1 and 2, Okay, so the concentration of X went up by 2. 0.005 times 2 would be 0.101. So this doubles between 1 and 2. This has to stay the same. And then this went up by a factor of 4. So the rate here quadrupled. All right, so I know that the concentration doubles here. So it went up by a factor of 2. And the rate went up by a factor of 4 as a result of that. Well, 2 to some power equals 4. It has to be 2. So that means that X would be a second order in the reaction. All right, so now let's look at the other one. Let's look at Y. So for Y, let's see. Okay, when I look at experiment 1 versus 3 here, well, in 1, it's twice as high as 3. So we're going to look at experiments 1 and 3 here. All right, so when the concentration of Y goes up by a factor of 2, so I'm going to look at this experiment compared to this one. So this one, it went up by 2, so the concentration doubled. Okay, so now I need to be careful about how I'm looking at this. So it doubled here. So from 1 to this experiment, it went to 1. So the rate actually stayed the same here. All right, so I know that my concentration went up by a factor of 2 when I compare this one to this one, but the rate stayed the same. Nothing happened, so it's just 1, because it went up by a factor of 1. 1 times 1 would be 1. So X has to be a power of 0. Anything taken to the 0 power is going to be 1. So X is equal to 0. And you plug that in your calculator, you'll see that it will be 1. So that means that Y is a 0 order. All right, so now let's write out the rate expression. All right, so we know that the rate, I'm going to write it right here, is equal to K, some K, multiplied by the concentration of X, which is the second order, so to the power of 2, times the concentration of Y to the 0 power. Well, anything to the 0 power is just 1. So really, the rate law is just this. Rate is equal to K times X to the power of 2. Y doesn't impact the reaction rate at all, so I can leave it out. Any kind of 0 order steps can be left out, because if it's taken to the 0 power, it's just 1. All right, so this is my rate law. Now, it's asking for a value of the rate constant and the units, so I need to actually solve for K here. So what I can do is I can just pick any experiment. It does not matter which experiment you pick. You can pick 1, 2, or 3, and then plug those values into this expression and solve for K. So we're just going to simply pick one. Let's pick 1. Experiment 1. We're going to use that data and plug it into this expression. So my rate here is 1. So 1 is equal to K. I don't know what K is yet. Times the concentration of X, which is 0.005 to the second power. Yeah, so I can do this. I can solve for K now. 0.005 to the second power would give me 2.5 times 10 to the negative 5th. Well, if I want to get K by itself, I'm going to divide both sides by this. And just solve for K. So K would be equal to 40,000. And that's a rather large number, and that's okay. All right, so 40,000 is the value of K, but it's also asking for the units. Remember, I told you that the units will vary for K. It depends on what type of reaction you have, if it's 0 order, first order, second order, whatever. So we need to figure out what the units should be. So what I like to do is I like to say, okay, my rate equation is this. Well, rate in this case is measured in moles per minute. So anything taken to the negative first power just means it's on the bottom of a fraction. So really what this is, it's the same thing as this. Anything to the negative first means that it's underneath the fraction bar. So it's moles per minute. So if I had m minus 1, that would mean 1 over m. It's the same thing. All right, so now let's figure out what it should be, what the units need to be. All right, so here's what I like to do. Okay, I know that the rate has to be measured in moles per minute. Well, the rate is equal to K, so I don't know what K's units are. That's a mystery still. But I do know that X is measured in moles per liter. And that's also squared, so big M times big M, moles per liter times moles per liter. Well, I know that for my rate, I have to have just 1 moles per liter on the top. So that means I need to get rid of one of these. Well, in order to do that, I can have a moles per liter on the bottom and get rid of them. Well, I also need a minute on the bottom. So a minute needs to be on the bottom. So it's just 1 over big M and mn, or minute. So 1 over m minute. So really, the units should be m moles per liter to the negative first, minutes to the negative first. Now, if you don't like my method of figuring it out, I'm going to tell you what the units should be for each type of order. And you can memorize that if you want, but I'm not a big fan of memorizing, so that's up to you. All right, so if I cannot reason my way through the data, I can actually just solve for everything mathematically. I can solve for all the exponents, I can solve for K with math. So what you do is you pick 2 experiments of data, and one concentration has to be the same. You're going to plug in known values for the concentrations. So you're going to take the data, plug in the concentrations into the rate law, and of course you don't know what the exponents are, you don't know what K is. Then you're going to divide the rate of one experiment by the rate of the other, bigger by the smaller usually. Cancel things out, cancel things out that are both on both the top and the bottom. You're going to solve for one exponent and then repeat for a different exponent using a different set of experimental values. Once you have the exponents, you can just simply solve for K, like we just did. All right, so the units of K, if you have a 0 order, it's either going to be your molarity divided by your time unit. So it could be seconds, minutes, or hours, it depends. But it's always going to be molarity divided by the time unit. For the first order, no molarity, just 1 over the time unit. So remember, if it's to the negative first, it means 1 over a second, or 1 over a minute, or 1 over an hour. That's what it means. If it's to the second order, it's going to be 1 over moles per liter times multiplied by the time unit. And then if it's second order, it's molarity to the second power times the time unit under 1. So this is the same thing as saying this. Okay? And the time unit will vary based on whatever you're looking at. So if you want to, you can memorize this, but I like to kind of reason my way through it. All right, so let's look at this. We're going to deduce the orders of the reaction, find the overall reaction, the rate equation, and the value and units for K. So instead of doing it with reasoning, I'm going to go through and do it with math. So what you do is you take the rate of one experiment, and you plug in the numbers that you do know for the concentrations of your reactants. And then what you do is you take another experiment and you divide it like this. So the rate of some other experiment. And then what you can do is you can cancel out anything that's the same on the top and the bottom, and then simply solve for one of the exponents. So I'm going to show you how to do this. Okay, so let's look at X first, or A first. All right, so when I look at experiment 1 and 2, I'll see that B is kept the same, and then right here, this doubled. Okay, so if I want to solve mathematically without reasoning through it, what I do is I take the rate of 1. So I take all the data and I kind of plug what I know into the formula. And then I take the information I know from the second experiment and plug it into the formula. And I divide one by the other. So I like to pick the bigger rate to go on the top. So let's look at experiment 2 first. So experiment 2, the rate is equal to 2. Remember, I'm using this. Rate is equal to K times the concentration of A to the X power. Okay, so I'm going to plug in the values that I know into this equation using experiment 2. So 2 is the rate. I don't know what K is yet. The concentration of A for 2, experiment 2, is 0.01 taken to some power, which I don't know yet, multiplied by B, which is 0.025, taken to some power, I don't know. And then what I'm going to do is I'm going to divide this by experiment 1. So the rate in experiment 1 is 1. K, I don't know. Concentration of A, in this case, is 0.005. I don't know what X is. And Y is 0.025. All right, so this is what I do. I take one experiment and I plug in the values that I know for the rate expression, and then I divide it by another experiment using the data that was provided. Well, I always pick the larger rate to go on the top and then divide it by the smaller one. It just, mathematically, it's just easier. All right, so anything that's the same on the top and the bottom will cancel out. Well, K will be the same, so I can cancel that out. And if I look 0.025 times, or to the Y power, so on the top and the bottom, it'll be the same number. I can cancel the whole thing out there. What I cannot cancel is this, because it's not the same on the top and the bottom. So now what I can do, since I've simplified it, is just start solving. 2 divided by 1 would be 2. 0.01 to the X power divided by 0.005 to the X power is the same thing as saying this. All to the X power. Okay, so 2 is equal to 0.01 divided by 0.005. So that's going to be 2 to the X power. Ha! And now it's much simpler. So X should be the first power. So I know that A needs to be a first order. All right, well, we're going to do the same thing to figure out what Y is. So I need to know what power B is being taken to. So now we need to look at what happens when I double Y. All right, so let's look, or B, I'm sorry. So right here, if I'm looking at this, 0.0125 is about half of 0.025. So I can look at experiments 2 and 3. Oh, actually, no. No, I can't look at 2 and 3 because these values are different too. So I'm actually going to look at 1 and 3 because right here it's 0.025 and here it's 0.0125, so doubled here, but this needs to be the same. A has to be the same, so I can't use 2 and 3, I'm going to use 1 and 3. All right, so I always do the bigger rate first. So 1 is the rate, K I don't know, multiplied by the concentration of A, which is 0.005, to some power. I can plug it in. I know it's 1 now, but it really doesn't matter. And then multiplied by the concentration of Y, which is 0.025, or the concentration of B to the Y power. Divide that by experiment 3, 0.5 is equal to K, multiplied by the concentration of A to the X power, or I could put 1 in since I know what that is now, it doesn't matter. 0.0125 to the Y power. Okay, so now anything that's on the same on the top and bottom, I can get rid of it. K is the same. This is the same. So now I can solve for Y. 1 divided by 0.5 would be 2. And this divided by this was the same thing as saying this. To the Y power. Okay, so 2 is equal to 2 to the Y power. All right, so again, our exponent is going to be 1. So this will also be the first. Okay, so now that I have that, I can solve for K. I have the exponents now, so now I can just simply plug in the data of one experiment. It does not matter which one. Any experiment will be the same value. And then just solve for K. So let's pick, I don't know, experiment 1. So experiment 1, the rate is equal to 1. K, I don't know, I'm solving for that now. Multiplied by the concentration of A, which is 0.005, to the first power, multiplied by the concentration of B, which is 0.025, to the first power. All right, so 1 is equal to K times this, and I get 1.25 times 10 to the negative 4th. All right, so now divide both sides by this. All right, so K is equal to this divided by this, and you should get 8,000. All right, so now I have K, now I need my units. So again, you could go through and just memorize the units, or you can reason your way through it. So let me reason my way through this. Okay, my rate is measured in meters or moles per liter per second. And I don't know what the units of K are, but I do know my molarity is measured in moles per liter to the first power. So that'll just be molarity, multiplied by my concentration of B to the first power. All right, so I know that I need just one molarity, so I need to get rid of one of these molarities. So molarity needs to be on the bottom, so I can get rid of it. And then I also need a second on the bottom. So it should just be moles per liter to the negative first and seconds to the negative first. Or you can just memorize them, whatever way you prefer. All right, so now let's look at something else. Let's look at mechanisms. Okay, so if I know what the rate law is, and I know some possible mechanisms, I can figure out what mechanism is more likely. So let's look at this. I know the rate law here is K times the concentration of A to B. So this is the last reaction we just did. So the first mechanism is this, and the second mechanism is this. So we need to figure out which one is more likely. Well, let's look. If I know the slow step, I can figure out the rate law just based on the slow step. So if I'm just looking at this one, the rate, if this was correct, the rate would be equal to K times the concentration of A to the first. Well, that's actually not our rate law. Okay, so if I know the mechanism and I know the rate determining step, I can figure out the rate law based on that slow step. And this does not match this. So let's look at the next one. Okay, the slow reaction here is this. So my rate in this case would be equal to K times the concentration of X times B to the first power. Well, it almost matches, except for this X right here. Well, if I look at the actual mechanism, X is an intermediate. I make X in one step and then use it in the next. And since X is only dependent on A, I can substitute. So it would be the second mechanism. And the reason I'm doing this, I'm taking X out, is because it's an intermediate, which are hard to measure. And since X is only dependent on A, I can just simply substitute it.